Good afternoon to all of you, and welcome to today's seed funding webinar. And the webinar is on EPITONIC, which is about enhancing performance and energy efficiency of Tsetlin machines through non-volatile computing. So I'm really pleased to introduce our speaker today, which is Dr. Shounak Chakraborty. He is an assistant professor at the Department of Computer Sciences at Durham University, England. And Dr. Chakraborty's work focuses on high performance and energy efficient computing with expertise in non-volatile memory technologies, computer architecture, and next-gen compilers. He has worked extensively across both academia and industry, and he has worked as a computer system architect as a zero-point technologies, for example, in Sweden, where he contributed to advanced memory and computing systems. He has published widely in IEEE and ACM venues as well on similar topics. So today he'll be sharing insights from the EPITONIC project, which explores how non-volatile computing can improve the performance and energy efficiency of Tsetlin machines. So with that, I will hand it over to Dr. Shounak. So we'll all listen to him now. So Shounak is on you now.
Thank you both. Thanks, Megan, and thanks, Ali. So thanks for the nice introduction. And thanks for inviting me for presenting my work. Now, could you please let me know, are you able to see my screen?
Yep.
Yeah, perfect. Okay.
Yep.
Hello and welcome everyone. So let me present one of the recent work that we have done from our April Hub seed funding this year. That is thermal modeling of magnetic RAM-based cache memory. So we had a plan to develop our thermal model for the cache memories built in some magnetic RAM. Let's take a look at how this magnetic RAM works. So on the right-hand side of the slide, you can see there is a small window. So where you can see the MTJ is shown. MTJ practically stands for magnetic tunnel junction. So we are mostly focusing on the spintronics memory. So the MTJ is actually the basis or the construction pillar for these spintronic memories. And these MTJs are actually attached with some of the substrate or some transistors to work upon. So mostly the circuitry is prepared with one transistor along with one MTJ or magnetic tunnel junction to store one bit in the memory. So these magnetic memories could be of two types. One is called as spin transfer torque RAM or STT-RAM. Another is spin orbit torque RAM or a SOT RAM. So just because of the compatibility and scalability issues, we have decided to go with the STT-RAM, not on the SOT RAM. And STT-RAM, out of all kind of non-volatile memories, they have shown some kind of promise in terms of designing caches. Like they have actually higher endurance, also better thermal stability, and also lower disturbance error, and also lower write cost when you're comparing them with the other non-volatile memories like phase change RAM, maybe with memory stars, racetrack memory, and so on. So specifically, while comparing the spintronics memories or STT-RAM with the conventional SRAM design, you can see that these RAMs, just because of the lower number of transistors available, so they have actually lower leakage power, and they are also highly area efficient. So, from this diagram, you can see that the one large size is used for the transistor, where MTJ is really small in size. And for storing, in case of conventional memory, we use actually such kind of transistors 6 times or 60 for the 60 cells to store one bit, where here you can see just one transistor is needed along with one MTJ to store just one bit, and where the bit can either be 0 or 1 like conventional systems, and we can actually define 0 and 1 based on the polarity of the magnets. Right. So compatibility is one of the most important part here. So how compatible these magnetic RAMs are, magnetic devices are, along with the field effect transistors, and STT-RAM, they are actually highly compatible while we are comparing them with the other memories in the same family. On the other hand, despite of having this high level of several advantages, they have actually come up with some kind of downsides like write energy and write latency. So both of these write costs are actually quite high for them while you are going to compare them with the conventional SRAM-based design for the cache memories. So to combat these things, we have actually designed several kinds of techniques, but unfortunately, no thermal models are actually there in the they're in the market for which could be used to study the thermal stability or several thermal properties. All these spintronic memories. These since their magnetization is or this magnetization of these spintronic memories are highly guided or highly defined by their current thermal status. So we decided to find out this kind of issues in the cache memories, and for that we have decided to develop a simulator for this one. And the problem was the right induced self-heating triggers the hotspots. So why these hotspots will come? So we'll see this one. And the gap was the standard tools, as I mentioned, like hotspot or NVSIMs are there. So NVSIM actually is a power simulator with which you can actually derive the power for your underlying non-volatile memories. They have some cell libraries induced there, and also you have the hotspot. So hotspot is conventional. Hotspot is actually designed for conventional field effect transistors, actually for MOSFET, but not for the FinFET or GAFET or no other state-of-the-art tools at the moment. And these tools, these memory-based tools like NVSIM or Cacti, they are actually blind to the submat gradient. So everything they have at some submat gradients, not at the very byte or bit level. So your submat can have a size of very close to 2 KB to 4 KB in size. So as a result, what will happen? So reliability practically sinks. Reliability sinks. The cause actually silent data corruption. That is at high temperature. This write cost will again further increase for this STD-RAM. That is write energy and latency, and that will generate further high temperature, and hotspot will come into the picture. And once you have the high temperature of these spintronic memories, they will actually compromise with the magnetization or other non-volatile properties. And as a result, you can have a high probability of getting some read disturbance error or some bit flipping error in place. Well, so we have started addressing this by bridging the gap between gap between device physics and system architecture, enabling a byte level power analysis and thermal tracking at 4 KIV granularity, which is actually required for capturing the submat thermal gradients. And our primary contributions of this work are as follows: so bit flip accurate power modeling. And then we have done some fine-grained thermal resolution, and followed by that, the last contribution, but not the least, is spatiotemporal reliability vector. So let's take a look at the STD-RAM MTJ. So this is how the MTJ actually looks like. So starting from the top electrode MgO cap, magnesium oxide cap, then you have the free layer, you have the magnesium oxide barrier and polarization enhancement layer, crystallographic diffusion spacer, and followed by that you have reference layer, anti-parallel coupling layer, fixed and seed layer. Okay, and this is when you are going to design the entire memory, you need to prepare a crossbar. So this particular MTJ will actually be attached with one transistor. That's what you can see in this right-hand side diagram. And they will actually be attached with source line, word line, and bit line. So source line means you are sending the source voltage there or the current source, and you have the word line there, and you have bit line as usual like normal RAM or normal cache memories, right? And you have actually input and output like VRead, VWrite, and V minus VWrite, and on the other hand, you have the sense amplifier, so through which you can actually read the data from this from the storage. Right, and we have actually divided the entire cache into small chunk of 4 kilobyte, and at which granularity we have actually generated the temperature to capture the spatial and thermal variation across the entire cache area. Why so? Because the LLC access pattern, if you see at the high level computer architecture, you can see that the most of the modern application since long back, they actually are they actually expose a specific property called as locality of reference when in terms of cache memory. That is, suppose this can be two types. One is called as temporal locality, and another is called as spatial locality. So when you are basically accessing a particular data multiple number of times over time, so it's actually called as locality of reference for temporal locality. And when you have the nearby locations will have the higher access in future, that is called as spatial locality. A very good example is the array. Suppose you are accessing sequentially the elements of a particular array. So you can see that the induction variable that is for I is equal to 1 to 100 thousands or so many number of times, the same I is accessed number of multiple number of times. That is can be a good example of temporal locality, while the sequential locations within the array could be actually defined as can actually defined as a spatial localities example. Now this locality of reference implies that some particular places in the cache will have actually high power density because of the access, and they will actually come up with some kind of hotspot, and this is called as actually localized hotspot, and this hotspot will actually degrade the thermal stability. As I mentioned earlier, that if you have high temperature, you're going to lose some kind of performance or some kind of non-volatile properties. So studying of the thermal stability is quite important, and we need to make sure that we have some certain design where thermal stability is actually at the same level or same type for the entire cache memories, for which we need to define, we need to design, come up with some kind of novel techniques, but that could only be possible when you have the access to the localized hotspot and how they are distributed across the cache area. And this simulator is actually going to solve the issue by showing these things, that how the spatial and temporal thermal variances are there across the entire cache memory. However, this thermal stability will actually create some kind of issues related to retention time, write endurance, and write cost. Write cost implies that the write energy and write latency, as I mentioned earlier. And retention stands for specific, the entire term is actually retention time. So what is retention time? So retention time means there is a certain time. So when you are writing a particular data at some particular cache cell, how long that data will be retained in that particular area without getting any disturbance. So that's called actually retention time, and this is actually defined at the design time when you are just before deploying your entire hardware for commercial purpose or maybe some other purpose. And when you have the high temperature, this retention time will be reduced. Retention time has come up with several different induced properties, so I'm not going to go for the details of these retention zones. Now I'll give you a bit more background. So when we have drill more about this background, so we came up with some of the physical property of the entire things. That is, the first one is the critical switching current, and this is the equation for this one. Followed by that, we have the several thermal stability. Thermal stability is actually defined by some energy barrier and Boltzmann constant, and of course it depends upon the temperature. So capacity transfer temperature for all these equations, and then we have the retention time. So tau is the retention time, where tau 0 represents the initial retention time that we have actually seen for some of the particular temperature, and that will have actually that is actually strictly depends upon the thermal stability, which is actually delta. Right, then we have the write latency. So write latency, you can see that this also has some kind of dependency on the thermal stability, and that has some inverse kind of dependency. Like if you have the higher thermal stability, high temperature, the thermal stability will actually you have the high temperature means your thermal stability will go down, and if you have the lower thermal stability, then definitely your write latency will actually go up. And you have the switching current like this one that does have some dependency on the temperature, and all these 5 equations are basically construct the heart of the entire thermal reliability dependency model used in this work. Now I'll give you the simulation workflow from the computer architectural viewpoint. So starting from the GEM5, so we have used GEM5 in for our simulation, and GEM5 is actually a full system cycle accurate simulator. So which we have modified at the architectural level, especially at the cache memory. So for extracting the byte level information, and that information is actually sent to our power model. So we are basically studying the LLC or last level cache here, for which number of reads, number of writes, and number of allocations has been have been collected at a periodic interval of 1 million clock cycles, whether our clock frequency was actually 3.0 gigahertz. Yes. And byte level, now our power model is actually designed to generate 2 kinds of power information for this entire cache, like dynamic and static. So this will be actually generating the power at byte level. So static power, we have actually defined it in a different way than the prior simulators, because all of the prior simulators for the memory at architectural level were based on the cacti model, and cacti model has some issues with computing the static power by adding some kind of randomization and assumption, and it could not it did not have the model for in between temperatures for all temperatures. Just they have some limitations of doing it for the 300 to 400K with a scale of 10 degree Celsius or 10 Kelvin. So we actually solved this one, and also resolved some issues like piecewise linear approximation, all those things. We have removed all this part, and we made it a bit more accurate by doing it at the byte level. And we have successfully captured the bit flip XOR logic as well as the MTJ asymmetry mode. And this will actually, once this power will be generated, these power traces will be actually sent as one of the outputs of the entire simulation framework, as well as we are sending these periodic power traces at byte level to our thermal model. Now for thermal model, to make it computationally a bit more feasible, we have transformed it from byte level to 4 KIB granularity, which is actually one of the optimal choices that we have already shown in some of our papers published last year. It's called as hot ReRAM, where the thermal model was designed for the ReRAM or ReRAM-based caches or for memory star-based cache memories. And followed by that, this thermal model will actually develop the power at first 4 KIB chunk that is actually derived from the byte level power. Followed by that, we'll have the lateral heat transfer and vertical heat transfer, like heat exchange with peers, and you have the heat abduction by the ambient. So basically, three things for the power dissipation, for the temperature has been considered here. That is the heat exchange among the peers and how good your cooling system is to abduct some of the heat from your circuitry, and of course the power consumption, right? So these three things are the most important, as well as the sufficient thing to calculate the temperature of your underlying circuitry. However, once we have the temperature, we are now sending these periodic temperature traces at 4 KIB granularity to one of our models that is called as reliability vector engine, and also we are sending this as one of our outputs that is called as periodic thermal traces. And this temperature also plays another major role by sending them to the power modeling model. So power modeling module is actually computing the static power, and you know that the temperature is one of the important factors that actually determine how much static power it will basically be consumed. Right. So once we have all this data available related to power and temperature, we can now compute some of the parameters, like which are the most important ones. So starting from the thermal stability, as we have seen from our earlier background study, that retention time, write latency, write energy, and mean time to failure or chip failure rate has strong dependency on the thermal stability. So now we have all these 5 parameters along with the power traces and thermal traces. And this is the entire model, that is a thermal model that we have prepared for this particular work. Now, for physical modeling and floor plan, so in previous slide you can see that we have talked about the heat exchange laterally as well as vertically. So this horizontal and vertical heat transfer will now be modeled by using some kind of floor plan. That is actually one of the construction pillar of the entire simulation framework. So floor plan is actually critical for 3 different reasons. So first one is the STDRAM reliability, that is actually intrinsically localized just because of the locality of reference that you can actually determine by running some kind of applications at architectural level. And secondly, the high density arrays facilitate lateral heat transfer between the neighbors. And also one of the most important factor in this case is that STDRAM or MTJ devices, they have very poor lateral heat transfer among the peers, but still they have some kind of heat transfer, which we have actually modeled here. Next, we have actually 2 different layers. So one is called as front end of line, another is called as back end of line. So front end of line is actually built up with some kind of copper delivery network along with the transistors that can have actually different kind of parasitic Joule heating than the back end of line, which is actually constructed by MTJs. Okay, so we have actually successfully modeled all these things, and this is how our floor plan looks like. So on the left hand side, you can see we have shown how lateral heat transfer will take place, and this is what we have actually modeled at the 4 KIB level, just because of the to make our entire simulation a bit more computationally feasible. On the right hand side, you can see that the vertical heat transfer. Okay, so starting from the heat sink all the way down to the contact and metal. In between, you have the heat spreader, thermal inductor material, and you have the silicon substrate, MTJ layer, and so on. So MTJ layer is actually the back end of line, where silicon substrate is actually the front end of line. Now, this is our evaluation part. So where the baseline system configuration will have basically 4 processor cores from x86 family, and we are using 2 gigahertz of clock speed, and it is out of order, of course, as most of the modern processors. And then we have the L1 instruction and data caches, which are basically the private caches. Followed by that, we have L2 caches, which is LLC or last level cache in this case, having a size of 8 megabyte STDRAM, which we have actually discretized into 4 kilobyte grid of 2048 in numbers. That is that this grid has actually 32 into 64 different chunks like that. And memory we have considered at 4 gigabyte DDR4 2400, and then ambient temperature we considered as 47 degrees Celsius. That is practically the just outside temperature of the case. And this is what we have received from our simulator, the temporal variations of maximum spatial and maximum spatial thermal variance across FEOL and BEOL. Okay, so this is the maximum spatial thermal variance across over time. So we have the data for spatial thermal variance as well as the temporal thermal variance, and stream cluster has the highest one and fluid anima has the lowest one. So we have actually plotted these two graphs here. And maximum and average spatial thermal variances across the parsec benchmark for front end of line and back end of line layers you can see in this particular graph. And then we have some other parameters like peak temperatures for all these 9 benchmarks. Then we have the write cost and retention time. So write latency, write energy, and retention time has been plotted in this graph. And finally, we have the mean time to failure over the baseline. And main results, actually, it shows that 11.7% write latency inflation along with the 20.7% dynamic write energy override and an exponential data retention decay down up to 65.7%, which is significantly high. And that's why I think this simulator is actually relevant for the industry as well as for the academia. And in conclusion, I can say that this work bridges a critical gap in thermal simulation of microarchitectural components designed with STT-RAM or Spintronics RAM. Then we have the results highlight that critical need for byte level physical tracking to avoid any kind of catastrophic silent features in resilient cache design. And our future work will, of course, include the logic along with some inclusion of the workload aware mapping, adaptive refresh, and multi-retention configurations where the entire cache will have multiple retention zones, because high and low retention zones, they have come up with different properties. And while exploring the machine learning surrogates to bypass RC solver complexity for real-time thermally cognizant optimization, this work is actually in progress where we are employing machine learning surrogates like some of the models like LSTM, Tsetlin machine, and of course we are using the DNN. So this work is actually under exploration. And I must thank to my student, project student, level 3 project student, that is his UG project. This was actually his UG project of Aditya. And of course, I am also thankful to April Hub and Dr. Sukar Agarwal from India and Dr. Thanasin Bunnam from Thailand. So they have also they are also one of the most important contributors to this entire work. Thank you very much.